Okay, this is the review for the GIS 200. Couple of things off the top. The vocabulary words that I gave you over the course of the semester, there was a data set with 60 different terms. That those 60 terms will be part of your final exam, so it is important that you know those as well, in addition to what we're going to cover on the slides. So, without any further wasted time, let's get started. What is spatial data? Information associated with a specific location, better know that. Discrete objects is important. You need to know what a discrete object is. You know, something either is or isn't. Continuous surfaces is another type of thing that we collect data on. That's something that's like elevation that we can just measure and keep measuring at different places. When we store data, spatial data is like a physical location, a shape, or an extent of something. The attributes is information associated with that spatially defined object. You need to know what those two things are. You need to understand the difference between rasters and vector, what each of those are, points, lines, polygons, as opposed to evenly spaced grid of data. It's a good idea to have some understanding of what makes up the various forms of vector data, and same for rasters. It's always a good idea to know the strengths and weaknesses, but I don't think I specifically asked a lengthy question on this, so I wouldn't focus too much there, I don't believe. Data models, two types. You better know both of these, spaghetti and topological, and what the differences are, and it's right here in the text. You need to know what topology is. Scale is important, and I don't think I got a specific question about that. Quality and accuracy, you need to know what data quality is and how it's defined. You need to know what metadata is. Path names are important, and so are file names in general, so it's always a good idea to know all those clever little things that you do and do not want to do when naming GIS files. You need to know what the different types of coordinates are. Here's a nice example of what latitude and longitude look like in terms of a GCS, a geographic coordinate system. Just another illustration of it in case it didn't make sense. First law of geography by one Waldo Tobler is always important. Hopefully you'll remember that. Everything is related to everything else, but near things are more related than distant things. You need to know what spatial autocorrelation is, and that it's basically what Waldo just said. Topological consistency, how well our GIS models mimic reality. Symbology, how we symbolize our data in the GIS. When we classify our data, there's different techniques. You need to know some of these. Specifically, you better be able to explain natural breaks and quantiles to some degree of efficiency. Some examples of what they look like. What is geographic phenomena? That's something that occurs in a place or a location that we can measure. Different types of maps. Not going to ask you anything that's going to come off of this specifically. Or this. This basic process of map making, you need to kind of understand it. I'm not going to be like super strict on how many spots you have, but the general process of taking data, creating some kind of a layout, symbolizing it, reviewing it, making changes, and then going around the cycle again and again and again until you end up with your final map. Basic layout, the components that go in a map, you need to know these, as well as the parts. Data frame, legends. Let's see here what else we got. Symbolizing your data, just general idea. Use things that make sense, colors that are easy to see and easy to read, and that fit what they're looking for. Don't make water brown, don't make the earth blue, the ground blue. Who do you get to review your draft map? Basically anybody but yourself. When you're making maps, certain things help make them better. Visual hierarchy, in other words, placing things that are more important in a more prominent position. The rule of thirds, not lining something up dead center to the middle. Utilizing negative space, in other words, those empty spots on the map. And balancing your items, and so that your map doesn't appear to be heavy in any one direction. Maximum levels of gray at 5 is kind of important. I can't remember if it's a test question specifically, but it's something you need to keep your mind on. Hey, made it this far without yawning. Quit complaining. Basically, human mind and eye has the capacity to differentiate between about 5 different shades of gray with relatively high accuracy. But when you exceed 5 different shades of gray, it becomes more and more difficult to distinguish which shade of gray on the map corresponds to which shade of gray in the legend, and so that's why we want to keep it at that or less. Coordinate system stuff is always a big part of your early GIS classes, because the problems that coordinate systems can create don't go away, and your level of understanding is only expected to improve and increase as you take additional classes. So as your first really true GIS class, this is the first opportunity we have to make sure. So there's 2 basic types of coordinate systems: geographic coordinate systems, which could also be called unprojected coordinate systems, and then the other type is projected coordinate systems. The GCS is spherical coordinates. Think of the globe and the angular measurements, like degrees, minutes, and seconds in longitude and latitude. Whereas projected coordinate systems are 2-dimensional maps. They're mathematical in origin, and they typically are going to be in meters or feet. Remember, every PCS is based on a GCS. Multiple PCSs can come from the same GCS, but that doesn't work the other way around. You can't have multiple GCSs work for a single PCS. It just doesn't work that way. Spatial reference is basically all the information that you got to have in order to make something project properly. And here's what that includes: your datum or your GCS, your projection if it's projected, your storage units, your domain, and your resolution. How does GCSs work? Here it tells you. Why do we use them? Really simple. All PCSs are based on them, so they're the basis of every PCS, so we have to use them at some level. But they're also really good for sharing, because it allows the user to convert them into a PCS. In other words, you project your data from a GCS into a PCS, and you do so to the PCS of your choosing. And so oftentimes we share data in a GCS so that you don't have to go through the hassle of changing something from one projection to another, and thus potentially increasing the amount of distortions and errors that could be occurring. We can limit that to just one projection, and that's the one you make from the GCS that you got your data in. What's bad with a PCS? Why don't we use them for other things? 1 degree is 110 kilometers, and so you have to go to like 6 decimal places to get accurate measurements, and so we don't want to do that. Now, there's some questions on this, some matching, some true false, that kind of stuff, maybe even an essay or two. It's important that you understand this because this is the basis of all the geospatial stuff that we do. A GCS has to be based off a perfect mathematical shape because it's a angular degree system, and it kind of only works in that fashion. And so we use something called a spheroid, which is a mathematically perfect but not round object. It's like a round object that you mash on the top and the bottom. Think of it like sitting on a beach ball. Well, not me sitting on a beach ball. One of you skinny student types sitting on a beach ball. The Earth isn't actually shaped that way, though, so what do? Well, we look at something called the geoid, which is a gravity-based measurement of the surface of the Earth, and it kind of gives you this wonky-looking shape like you see here. This is called an oblate spheroid. It looks sort of pear-like, and that's actually the shape of the Earth, as best we can tell. So what we're going to do then is take this nice perfect mathematical shape that we have and make it fit to that. So how do you do it? You adjust the size of the north-south and the east-west axis of the spheroid so that it's in approximately the same size as the geoid, and then you move that center of the Earth point in the spheroid relative to the center of the Earth point in the geoid until each surface aligns with one another in the area that you're interested in. And once we've made that alignment, we end up with something called a datum. And a datum is simply where the spheroid has been made to fit to the geoid. And from a datum, we then create a geographic coordinate system, and from a geographic coordinate system, we can create a one or more projected coordinate systems. This just shows what I'm talking about. Lots of different types of PCSs. You need to know that there are more than one, like cylindrical, conic, and azimuthal, and what those terms mean. I'm not going to go into the cube, the fuller, and the Banach pseudoconic. That's a cylinder. That's a cone. That's azimuthal. Cylindrical projections. Most famous one is Mercator. Mercator did this like a forever and a long time ago, and his cylindrical projection was a simple one, and it was used for navigation because it preserved direction. The most common one that we have today is the UTM system, the Universal Transverse Mercator. Transverse means that instead of that cylinder going up and down, the cylinder goes sideways. So why do we like the UTM system? It's very accurate where the cylinder is closest to the Earth, and so because it's transverse, or running sort of sideways, if you rotate the cylinder, the point of contact between the cylinder and the planet, if you will, the point where it's most accurate, moves as you rotate the cylinder. So we divide the Earth up into 60 zones, and within each zone, when we rotate the cylinder around to that location, it would be 6 degrees wide, that zone, 3 degrees fore and 3 degrees aft of the line, and within that area, from pole to pole, distortions are minimalized. Here's an example of the transverse cylinder going around the globe. The line there is that point of contact. That would be in the middle of a zone, 3 degrees to the right, 3 degrees to the left, and that would be a single zone. And if you go the whole way around a planet, there's 60 of those. And those look sort of like this. Conic projections. The main thing with conic projections is to remember some of the names, like Lambert, Albers are two of the most common ones, and that's about all you need to know there. Azimuthal projections are basically just flat projections. Compromise projections distort everything a little bit, nothing a lot. Anytime we take a round three-dimensional object like a globe and we try to make it into a two-dimensional object, it creates distortions, and you need to be aware of this and understand that and how it happens. When we talk about conic and cylindrical projections, there's two flavors, I call it, tangent and secant. You need to know what these terms mean, not just the written definitions, but to be able to look at it and see. And remember that these projections are most accurate at these points where these standard parallels, the tangent having 1 and the secant having 2, make contact with the surface. And here's what we're talking about. We have a conic projection, cone, over the globe, one standard parallel, the point where it makes contact. Along that green line on the left is where it's the most accurate. In a secant configuration, the cone is slightly smaller than the planet, so the planet intersects the surface of the cone. Where it goes out of the cone and where it comes back in, you get a standard parallel at each of these, and thus at those 2 points it is more accurate. You can adjust these things so that those standard parallels move closer or further apart as you need to make the map of your choice more accurate. Basic parameters of PCS, rasters, resampling. These are the 3 resampling techniques. You need to know how they work and what happens. And I'll give you the quick, brief rundown, and you should commit this to memory. You will have this on tests time and time again. 3 techniques: nearest neighbor, bilinear resampling, and cubic convolution. Nearest neighbor, fast. Cubic convolution, slow. Bilinear, in between. Nearest neighbor doesn't change anything. It just looks at the old cell that's closest to the center of the new cell, and it takes that value as is. Poof, done. Bilinear uses a distance-weighted algorithm. The reason I enunciate that way is because I want to make sure you hear me. Distance-weighted algorithm. If you don't say distance-weighted algorithm, the best you can do in explaining bilinear is get half the points. Distance-weighted algorithm takes the 4 closest cell centers from the old data and then uses a distance-weighted algorithm to average to get the value for the new one. Cubic convolution uses the exact same process as bilinear, except instead of 4 cells, it looks at the 16 cells. This creates data that is blurred or smooth because it's looking at this distance-weighted average across 16 cells as opposed to 4 cells, as opposed to only using the actual value of a single cell. And so nearest neighbor preserves the data set the most. Cubic convolution distorts it the most. Bilinear is somewhere in between. Common datums. I don't think I'm asking you a question about that. Most common coordinate system, geographic coordinate systems, because we use them for data portability. The other 2 that are most common in the United States are the UTMs and the state planes. The UTM is very good within an individual zone. The state plane or set the regions within states, and they work very well for the places they're designed. Large scale maps. At large scale, that means a small number on the bottom. It means a smaller number on the bottom. In other words, you're more zoomed in. And at large scales, you virtually have no distortions. Smaller scale maps mean you have a really big number on the bottom, which makes the fraction really, really small, which means you're really, really zoomed out, like 1 to 80 million or something. Distortions become obvious at these scales. You can make special projections just by modifying things like standard meridians and standard parallels. 2 most common types of errors with projections, you need to know this. The first one is you have no projection information, or the information that you have is wrong. And that's it. So what do you do to fix them? Well, if you don't have any projection information, you simply define it what you think it is and see if it fixes it. If it doesn't, you just define it as something else until it's fixed. The other problem we have, it's not really an error, is data is not in the projection that we want. Okay, we'll talk about that in a bit, but for now, when we have something that is projected wrong or doesn't have its projection information defined, we fix it using the define projection tool. Now there's a very similar tool called the project tool. The project tool is for changing data from one projection to another. This requires the data to not only be projected, but to have all of its projection information there so that you know exactly what it is and the software can read it. Then you can change it. The project tool always makes a new file, and the new file is always in the new projection. You use this tool to change projections. The define projection tool we use when we have missing or incorrect information, and all it does is modify the labels on the existing data. Doesn't change anything. All the numbers that are stored along with the projection, they stay the same. We simply change the label, which then instructs the software how to read those numbers, and if we change it correctly, things work, and if we change it incorrectly, they will not. Talk a little bit about basic editing. It really comes down to two things: editing something that already exists or making something new. The big thing here is to know that if you just start making stuff willy-nilly, you're going to end up with a spaghetti model. You're better off to have some topology rules in place and to utilize tools and things like that to create some map topology so that you end up with a better quality product. If you're going to make something new, the first thing you do is make something empty, and then you fill in the boxes, you fill in the blanks, you draw the feature, if you will. Logical consistency, remember what it is. It's how closely things in the real world are represented in the GIS. Is your intersection an intersection? Is it an overpass or an underpass or an actual intersection? That kind of stuff. What do we not want to do? We don't want to have dangles, gaps, and overlaps. And how do we fix those? We fix those by using things like snapping tools and setting our various tolerances so that we don't have those and we can avoid them. See, snapping and special tools. Coincident. Do things side by side, have a shared boundary. It's one boundary, but it's one part of each data set, so that when we modify one data set, it modifies it for the other. Think of this like county lines. The line between Fairfax and Loudoun County, for example. If Loudoun County moved their county line, it would only be right for Fairfax to move theirs accordingly. And so even though it's the terminal side border for each county, and it's a part of each county, it's also the same line. So when you move it for one, you should be moving it for the other. And that's what happens when you utilize some of this map topology and dealing with these coincident features. Now, some of these slides you're thinking, wow, he really just zipped through them. I kept all the stuff that was most important, and I went through and I tried to write questions. And what I'm trying to do now is go back through and think about the questions that I wrote so that I can steer you towards perhaps a more concentrated study. What I would ideally want you to do is look through all the slides that I gave you for the exam, this set that we're looking at here. Watch the video, listen to what I say, go back and study over the parts that I'm talking about and highlighting and studying and staying on, and then go back over everything again, just read through it. So in between a more focused study about what I'm talking about, read through everything, and then come exam time, it should be a relatively easy exam. Must remember is always have a backup, don't have more things open than you need, blah blah blah. Making something new, there's instructions. Let's see here, we've got geoprocessing. When we talk about geoprocessing, it's basic, but it's also powerful. And we're going to talk about overlaying, editing, and some of these other tools next. Map overlay, you know what it is. It's overlaying one data set over another. Ooh, shocker. Name actually means what it says. It is similar to a spatial join, but it doesn't excuse me, have any restrictions due to cardinality. Okay? Map overlay enforces a one-to-one cardinality where spatial joins require certain types of cardinality, and as the cardinality changes, The capacity with which you can create or construct a spatial join changes or is limited. Why do we use them? This is a really complicated way of trying to explain it. Basically, if things don't line up, spatial joins are awkward. Overlay functions don't care, and they just go do it. So some different ways it splits features up, ensures one-to-one cardinality. These are just some of the different overlay techniques. I don't think I asked any questions about that. Yeah, I need to talk about this for a second. Basic types of overlays: intersect and union. Intersect, you end up with the product of the two layers, basically common space. Union keeps everything from both data sets, in other words, everything. Intersect can be polygons, lines, or points, etc., etc. You need to know what clip does, what erase does, what intersect does, and what union does. If you understand these fully, that will help you a long way on the final. These are some illustrations of intersect and union. An illustration of what clip does. An illustration of what erase does. Alright, this is something that students struggle with, and I've explained it many times, and for some of you you get it, for some of you you do not. So let's take another quick stab at this. Say I've got a polygon that is the state boundary of Delaware, and that data is currently recorded in a geographic coordinate system. And I decide I'm going to project it multiple different ways. First as a conic projection, and then as a UTM projection. Now, when I do it in each of these, they have their own unique means of distorting things. Particularly, the UTM is going to distort the size, and the conic projection is going to distort the shape. Both of these are going to make those calculated values that we often see in polygons for their size change. Because if you take a shape and you bend it, the area inside that shape is different. If you take a shape and you stretch it in all directions, it gets bigger. Or if you squeeze it together from all sides, it gets smaller. Either way, changing the number that is listed for the size, or what should be. Now, here's the thing. That number doesn't change when you do these things to it. Okay? There is only one instance where those fields are updated after you make these changes. If what you're dealing with is a feature class in a geodatabase, then there are two fields, shape underscore area and shape underscore length, that could be updated and will be updated to reflect the accurate area or length of the polygon or line under the new projection. If we're talking about a shapefile, not a feature class, it's not updated. If we're talking about anything not in a geodatabase, it's not updated. If we're talking about a field called area and a field called length in a feature class in a geodatabase, they're not updated. Only shape underscore area and shape underscore length in a feature class in a geodatabase are automatically updated. In every other situation, condition, or description that you can come up with, those measurements of length and area change when the data is edited, modified, or projected, but the information in the attribute table is not updated. So always assume they're wrong and fix them. Other tools, not going to talk about them. Not so much about that either, or that. Map algebra, we'll talk a tick about it, knowing what it is. Applying math to different data sets. Just be aware that map algebra is not a raster only thing. It tends to be used a lot in raster, and it works really good in raster, but there are some versions of map algebra that you can do adequately with polygons as well. Cost, distances, and things like that are specialized rasters that measure distances from another set of features. And reclassifying is an important way that we change values inside a raster dataset. That's something that you need to know for a test question. Interpolation, need to know what it is. Filling in the blanks, basically. Taking the known data to fill in the unknown, to fill in the values at locations where we don't have any data. A couple of techniques: IDW, splines, and Kriging. You need to know about splines and Kriging, inverse distance weighting as well, but that's pretty basic. IDW, closer points, contribute a greater percentage in terms of the weighted average. Splines and Kriging, we're going to talk more about those in a slide or two. So there's IDW, relies on things like Tobler's first law of geography. The assumption is that points near places that you measure should have values near to the values that you measured at the place you measured. In other words, things are related to other things, but the things that are close together are more related than things that are further apart. Splines are based on polynomial math equations. They fit curved lines through all your known points of elevation. Forces the data to run through the points, but because of the nature of polynomial curves, you can end up with values that are higher than your highest and lower than your lowest. Kriging is a statistical way of interpolating, and it has a random element that goes into it. It uses something called a semivariogram to estimate the randomness of this and to give you some idea of how accurate your estimations are. It is a complex interpolation that was developed for the purposes of finding gold. And there are multiple parts: the nugget, the seal, the range, the partial seal, and all these are components in the semivariogram. We're going to look at a few here, and I'm going to tell you what is on the exam. This is the diagram, the nugget, the seal, and the range, and I'll sort of ask you to explain those parts in Kriging and what they are. And as you look at this picture here, you won't have the picture come exam day, so you have to be able to visualize this. Across the x-axis is distance between sample points, and on the y-axis it's variability. And so the nugget is just the basic variability that you have within the data set. Okay? The range is the distance between sample points when the variability hits its plateau or maximum. Okay? The seal is the level of variability in your data when you reach that range. Does that make sense? Alright, let's see what we got next. Surface analysis, we're going to talk a little bit about these. These are just basically big raster things that we do, like DEMs, and from DEMs we calculate things like slope, aspect, viewshed, and hydrology. Neighborhoods, block functions, focal functions, zonal statistics. Blocks are moving windows that don't overlap. Focal functions are moving windows that do overlap. And that's all. Zonal statistics utilizes a different data set to define a zone and then calculates statistics from all the raster cells within that area. Resampling. We've already talked about this a little bit. 3 techniques: nearest neighbor, cubic convolution, and bilinear. We talked about the process: distance weighted algorithm, 4 cells, distance weighted algorithm, 16. New value closest to the old value closest to the new value for the nearest neighbor. It's exactly the same thing I talked about 10 minutes ago. You have to know these. They will be a test question. Going to talk a little bit about the modeling process. Just remember how it works. Starts off with defining the goals, breaking it down into parts, basically figuring out what you need. The data is what matters, how much it matters, and how you put it together. You're going to sketch out maybe how to do that. Step 3 is you implement your model and calibrate it. In other words, you try to make it work and see how it's going to be in the real world. You do things like sensitivity analysis and all that sort of stuff. And at the end, you kind of validate it to see how it performs. There's 4 basic types of models, and I'm going to ask you some basic questions about them. Binary model, you need to know that uses logical expressions to select spatial features from a composite feature layer. Kind of a 1, 0, true, false, yes, no sort of map. And it's really common in siting analysis. In other words, where do I put this? Where is the best location for something? Index models are next. Index model calculates a index value for each unit area. Basically gives you a ranked map with these index values. The better the value, better location. Similar to a binary model in a lot of ways. Multiple criteria. Depends on overlay functions. But instead of just giving you a 1 or a 0, a yes or a no, it gives you some variation, some degree of maybe. Set up typically as a weighted linear combination. We have to do some work on it to do this. We have to figure out if each criteria is how they compare to one another in terms of their importance. And if they're not equally important, we have to determine how we factor in that. So we have to assign a weight to each one. We have to standardize our data so that we are on equal footing in terms of the numbers, so that our results aren't blown out by the scale of the variability of the data. And then we calculate our index values from that. Key things to remember: index, standardize, and weight. Just remember that the value itself doesn't mean anything. And we standardize because we have to, due to the issues of scale and how that can really blow parts of your model apart. And we weigh things because not everything is as important as everything else. Different techniques for standardizing: 0 to 1, dividing by the range, z-scores, and standard deviations. 0 to 1 is the most common. Here's the equation for that. I'm not going to ask you any of these equations, so I'm going to skip through the rest of these slides pretty quickly. Okay, now we're on to vector-based index models. Basically, if you don't have rasters and you have polygons, you can do this to the various fields in the polygon attribute tables. They'd use the overlay functions to combine and enforce a one-to-one cardinality, where you can then add additional fields and sum up the respective values and weights and other criteria standardizations to generate your index values on a polygon by polygon basis. And that's the gist of it. In raster, it's pretty much the same setup, it just looks different. Each of your inputs are individual raster layers. standardize the values. You multiply the values by the weights that you assign to each of those criteria to generate a new raster dataset layer that you then combine using some sort of a map algebra function to give you a new final raster output, whereby you can then assess which raster cells, but it's getting hard to talk, which raster cells are the ones that meet your criteria. And that's how it's done. Okay, next is the regression model. For regression models, you just need to know that it uses a regression equation to generate the values in your model. In other words, it takes some dependent variable and it relates a dependent variable to a number of independent explanatory variables excuse me, in an equation, and you can use this for prediction or estimation. We use two types, linear and logistic. Linears for numeric regression has a categorical component. And the last one's process models, which basically almost everything environmentally is a process model. I'm not going to spend any time talking much about it because a process model is very much like an index model, but it sometimes has binary model components and regression model components. And so really it's a combination of these three things to reflect natural processes that are and models that are based off of our understanding of the real world.